So now let's talk about the Lattice DMA IP samples. We founded a partnership with the Lattice. I believe it was a few months ago, something like a year. And then we got their devices, their cards, Avant and CertusPro-NX CP-NX. And we started to work with these FPGAs and developed samples for them, or drivers. That means that if you have these samples, these devices, you do not need to build a driver for it, because we've created this functionality. The same for a few Xilinx samples like XDMA and the Avalon memory map. So all our samples are essentially drivers for these devices, and we have a working application that can access these devices and perform tests and DMA, reading and writing, etc. So just a little bit about these devices. The Avant is a mid-range from the mid-range FPGA family, optimized to deliver the lowest power and highest performance FPGA devices in the class, the mid-range. It delivers the highest DSP and embedded memory to logic ratio for its class, and fast external memory support, LPDDR4, okay, at 1866 megabyte per second. The CP-NX, okay, has the lowest power and smallest package in this criteria, okay, versus similar FPGA. It has more on-chip memory and supports LPDDR4. The only FPGA in class with LPDDR4 support. Now we will deep dive into the samples. So the first thing, and we'll go from less technical to more technical. We will see how we can access these samples. So if you already know WinDriver, you probably know our samples folder. So if you don't know WinDriver, we have a samples folder that includes samples for Xilinx, Altera devices, PCI Diag, PCI Diagnostic App. Let's go into Lattice. An open CP-NX DMA sample. I will open it using CMake in Visual Studio. And now I haven't generated anything, okay? I'm only opening a sample that is available on our folders. CMake will build it. Just a second. Okay. And here we can see all the relevant files, okay, the code that we've created and generated for this sample. The function implementation. These functions are probably, you can find them on other samples. What I want to show you here is the header files, which includes all the definitions that this device, that enables the communication with the device. Okay, so we have the bits definition, we have the offset definition, host to FPGA registers and FPGA to host registers. We have the critical functions for this one to work. Okay, so on this one, so we have here everything you need in order to make this driver or this device work. And we can see here the kernel plugin. Again, the addition to the XDMA sample. You can build it. Build succeeded. Okay, I don't know what it failed. Let's see. Okay, succeeded. I'm not running the right one. Okay. And here we have it. Now I will fail. Why have I failed? Because I don't have the Lattice device or this device on my PC. But if you have, it will identify it. Okay? So again, you don't need to do anything, change the code. If you have this Lattice device, the CP-NX, connect it to your machine, and you have a working application running and available without even generating the code. If you want to generate the code, let's go to the wizard. Okay, it's on the second screen, just a second. Okay, I've created a new project, choose my device, generate code, choose Lattice Avant DMA or CP-NX DMA, and you can simply generate it. Generate your project. I won't generate a project in order not to waste more time. We have a lot to cover. So this is how you can access these samples. Both samples come with performance tests. We will see it. Customized DMA IP data. I've showed you the offset, the descriptors, interrupt handler, the DMA mechanism, kernel plugin to be incorporated in the DMA, and all the other functions. We're supporting both Windows and Linux. Now, let's see. We've opened the sample and generated the sample. The performance test. This one is new. It is included in the samples and the PCI diag. I want to show you a video of the performance test. Okay, just a second. Okay, CP-NX DMA performance. I know it's small. Okay, we will go step by step. Okay, this was opened in Linux, the CP-NX DMA diag. We can see one matching device. This is not the error I got because we have 12.4, 1204 is a Lattice vid. We have the vendor ID, device ID, we have the location, the memory bars, and we can see the device's info. Now we chose to perform a DMA. Wait, no, it's the perform. Yeah. To perform a DMA. Number 5, okay, we have the option to scan the PCI bus, find a specific one and open it. We chose 5, perform DMA. We can perform a DMA transfer. We can perform DMA transfer to device, perform the DMA transfer from device, and to compare them both, and to perform DMA transfer to device with incremented data, perform the DMA transfer from device, and compare the DMA buffers, or just measure the DMA performance. Okay, so in our case, we chose 4, measure the DMA performance. We need to choose the direction. We chose host to device performance. We can also choose device to host and to choose both of them, the host to device and device to host, running simultaneously. So after we chose the host to device performance, we need to set the parameters for the DMA. What is the buffer size? We said 128. The numbers of time, we chose 1000, and then click go. Okay. So now it is running the DMA host to device performance test 1000 times as we asked. And here we got it. The DMA host to device performance test transferred this amount of bytes in this much time with a rate of 193.44 megabyte per second. So this is an example of how to perform a performance test. Now we can see here that we've chose to perform simultaneously the host to device and device to host performance test. Number 3 entered 64 in buffer size and 100 repeats. And here we can see the results, okay, of the device to host and the host to device. So this is a great tool to test your device and its performance. Again, available on the user application. It can be the CP-NX DMA, Avant DMA, PCIe diag. Find it there, and you can test it yourself. The next thing we will talk about, and this is the most technical part, would be the DMA flow. If you don't have, or you don't know, or you don't understand some of the things that we'll talk about now, that's okay, because you don't need to know any of it. I'm taking you under the hood of our samples, okay? The samples were developed by our team. So you don't really need to know the specifics of everything that's going on in the background. But it would be nice to know what's the flow or what's going on, and it would be maybe good to know if you want to troubleshoot your driver. But it is all built in. Everything I'm about to explain now, it is all built in on on the user application. If you've been to the previous webinars, I've talked about the DMA. So you know there's a sequence. WinDriver allocates the user mode buffer, locking the physical memory to perform the DMA on top of, initiating the transfer, and notify when it completes. This is, let's say, a high-level overview of the sequence, of the DMA sequence performed by WinDriver. Now we will we will make like a zoom in and see what happens in the lower level of the DMA, and how our team, what's the architecture, okay, that our team used in order to make this DMA work with the CP-NX, specifically a sample of Lattice. So generally, when we're talking about DMA, we want to move data, okay, from one place to another, the source and the target. It can be it's the host and the FPGA, or the FPGA and the host, or not FPGA, just a device, but we want to move data. So in order to do that, we need to create components, we need to create entities. In this example, I will talk about a host to FPGA, okay? So here we have the RAM memory, and we here, ROM, the hard drive, and here we have the target, okay, which is the FPGA. And in order to start familiarizing, let's say, the target with the source, we need to create entities. And the CP-NX sample requires two types of entities. The Avant requires 3. I will talk about them. But most of our demonstration and discussion will be around the CP-NX sample. So we have the data entities or buffers and the descriptor, okay? And the descriptor is important. So what is a descriptor? The descriptor contains information on the metadata of the transfer, okay? The transfer length, the source and destination address, and the next descriptor address. So here we can see the struct that holds the info that the descriptor contains. So essentially, it holds the information regarding the buffers, okay? The data buffers and the next descriptor address. The descriptor is a contiguous memory that is allocated and locked. and we have the data buffers that we want to eventually transfer to the target, which includes only the transfer data. The information on the destination and the source and the length are contained in the descriptor. Okay, so again, descriptor buffer and data buffers. These are the two entities. When we're looking at the CP-NX DMA struct, we can see that we have the data transfer DMA buffers and the descriptors DMA buffer, which is contiguous. In Avant, it's a little different. We have one buffer for the data, scatter gather, and we have two buffers for the descriptors, for source and destination. And we have something that we don't have at all at CP-NX, which is the status buffer, which contains the status of the source and the destination. In CP-NX, the status is stored in the device. Okay, so we don't need to allocate a new buffer to hold this value or this data. And in Avant, this is not the case. So just remember it, remember the colors. It is a little different in Avant. We will probably have a webinar dedicated for Avant, and maybe another one for CP-NX, more in-depth. So now that we know what we need, and again, I'm talking about CP-NX only, source, host, target FPGA. We don't have these entities right now, and we need to create them. So the first thing we need to do is to allocate and lock the memory for the data. Only the memory. These memory buffers are not defined yet. So we're using the world famous WDC DMA scatter gather buff lock. Okay, this is for the data buffer. And okay, this is for the data. We said it is a scatter gathered, right? Scatter gather buffer. So we're using WDC DMA scatter gather buff lock. And for the descriptor, we're using a WDC DMA config buff lock. Okay, in order to create this data buffer, which will hold the metadata for the transfer. In Avant, we need to allocate and lock another entity, right, for the status. So here it happens as well. We're using the WDC DMA config buff lock in order to lock the source and destination status. So now we have these buffers. They don't have names yet. They don't have a purpose yet, nor not data and not descriptor, but these are just locked memory buffers. In order to give them their purpose, we need to configure them. So how can we do that? So we start by configuring the descriptor. The descriptor, as I said, is a contiguous buffer that contains the metadata for the transfer. And the descriptor it's not just one, but this buffer contains all the descriptors that the transfer would require. I will show you it soon. So if it had no meaning, now it has. Okay, I will show you how we are doing it, but it will contain the info it needs in order to become the descriptor. So here we are using the DMA transfer build function, okay, in order to configure the descriptors. And here you can see we are transferring or moving F2 device all the pages from source address, destination address that require the metadata of the transfer to the descriptor. So it will contain all the information it needs in order to perform the DMA transfer. Okay, so after we configured the device after we configured the descriptors, okay, or built it, now we need to configure the device with the descriptor's addresses. Okay, not the data that the descriptor holds, but only the addresses of the descriptor. So the target, which in this case is the FPGA, would know to access it and get the info once the DMA is initiated. So this is the next step. Write descriptor data to CP/NX. Okay, and here we can see that we are moving or introducing the addresses. Sorry. We are introducing the addresses to our to our destination. So this is the next step after getting all the information we needed to the descriptor, introducing the descriptor to the FPGA. When talking about Avant, we need to make the same with the other entity we have there, which is the status. Okay, so we need to configure the status that we've locked and allocated and locked the buffer to in the previous steps. So now that the device knows where to access in order to, or where to ask the DMA transfer metadata from, we can start initiating the transfer. In CP/NX, it is done by writing to an offset on the device to initiate the transfer. Okay, so there is a specific bit or offset that we write to in order to start DMA. Okay, and this is the struct CP/NX DMA start DMA. This is already defined. You don't need to change anything in order to start the DMA. So when you click start DMA, we will initiate the transfer. And then the next thing happens. Okay, the target, which in this case is the FPGA, is getting the information, reading the data addresses from the descriptor buffer. Okay, it is getting from the descriptor the information, the buffer's address of the data. Okay, because we said this descriptor, or in this case this one, contains the information on this segment. Okay, on this data buffer. And this way it can access this data buffer and get the data transferred. After this descriptor is done, it is passing and it holds the information on the next descriptor. Okay, and again, the next descriptor is giving the target, the FPGA, the information on the data buffer, and the target gets the data. And again, this happens with as many as buffers, data buffers the descriptor contains until it reaches the last one. What happens when the last descriptor finishes transferring the data it requires? The last descriptor sends the info and an interrupt is raised. Okay, an interrupt is raised by writing to an offset in CP/NX after the last descriptor is transferred. We talked about two types of DMA methods. The polling, where the CPU keeps asking, are you done, are you done, are you done, are you done, during the DMA, which is consuming resource and requires more reading and writing. And we have the interrupt-driven DMA, where the DMA takes place, and when it is done, the CPU is informed we are done by raising an interrupt, which is much more efficient in a lot of ways. So once the last descriptor ends, an interrupt is raised and the DMA is completed. Okay, So this is an interrupt-driven DMA we are talking about. And the next thing we need to do is to clean. CP-NX does not have a cleaning or a DMA stop function on the device. So we have the DMA close routine, which essentially what it does, it unlocks the the buffers and the offsets. Okay, so it unlocks everything, cleans all the memory, offset everything that we've captured and transferred during the DMA, and we return to where we started. Okay, we have a clean slate. The source and the target are now ready for another DMA. You don't have data left or scattered around uncontrolled. Okay, the routine cleans everything up. I want to show you how it looks like before talking about kernel plugin and showing the data. So here we have an example for CP-NX DMA, again running on Linux, simply opening the CP-NX DMA diag, getting all the information, and choosing DMA. Okay, now the option we chose is perform DMA transfer to device, perform DMA transfer from device, and compare the DMA buffers. Okay, and again, everything I showed you is just happening under the hood. All you have to do is open this application and click on numbers. This is the message, okay, the data again, slowly. This is the data pattern that we want to transfer. These are the numbers of packets, okay, we said 100. Enter the device memory address to transfer, okay, which you need to know according to your device. And now we are getting the information. It is now running the DMA using a kernel plugin. We have two interrupts raised. One interrupt is raised, the DMA transfer is completed successfully, and we have another interrupt that is raised. We see the buffers, okay, that we requested to send. The DMA transfer completed successfully, and we asked to compare the buffers. So write buffers and read buffers are identical. Okay. After finishing, the DMA interrupt is disabled, and everything again is happening in the background. You have the user app to be utilized as you wish. No, I don't need the Visual Studio. Let's go back to the kernel plugin. So remember when we talked about the kernel plugin, you have a kernel plugin already implemented in the CP-NX and Avant samples. This is the Avant code, as you can see. What I found important here is to emphasize that the kernel plugin is taking place in the kernel mode, as we said. So the allocation and locking is taking place in the user mode, and all the other functionalities are taking place in the kernel mode, which leads to a significantly more better, faster results. Okay, the interrupt is being handled from the KP, sparing the context switch. Remember when you talked about it? So here we can see some nice data in CP-NX. This is PCIe 3. We have tested the host 2 FPGA with kernel plugin in a single direction and without kernel plugin. And here you can see the results after 10 times or 10 routines, DMA routines, 100, 1,000, and 5,000. And here is the other direction, okay? FPGA to host with kernel plugin and without kernel plugin. You see more than 100% improvement, increase in the performance. In Avant, the numbers are less. Let's say the increase is not more than 100%, but it is much better. Around 70% increase is very nice. running the host to FPGA with KP and without KP in red, and FPGA to host with KP and without KP in green. The reason for this increase is the fact that the kernel plugin sits in the kernel mode. Now, in these tests, the interrupt was raised after each routine. Okay, so you have, let's say, you wanted to test it 100 times, so you raised 100 interrupts. You had, without KP, 100 context switches. And without kernel plugin, you didn't have 100 context switches, which is the improvement you see here. So the numbers don't lie. Kernel plugin is much faster, and it is built in your code. So you can utilize it without the need to develop anything new.